Good morning, everyone, and welcome to today's webinar. The topic is innovation in heat pump technology, and we will use this hour and a half to introduce the winning projects of the Heat Pump Award 2024. To give you a bit of an overview of this event's agenda, I will start by welcoming all of you and by giving you a bit of an introduction, a presentation about the next application cycle of the Heat Pump Award 2025. We will then move on to a keynote speech done by Kaven Norris from Frascolt, our sponsor. And then we will officially start with the presentations of the winning project, starting with the Heat Pump City of the Year Award, then moving on to the DecarBuilding Award, the Lighthouse Heat Pump Award, the DecarbIndustry Award, and finally the People's Choice Award. And at the end, we will have a brief Q&A where you will have the chance to hear from our speakers any response to any questions you may have. The questions, you can leave them in the chat. Please indicate the speaker you are doing the question to, and then during our Q&A at the end of the event, we will go through them. It's important for you to know that this event is recorded and transcribed, and please keep your camera and mic off. And as I just said, just use the chat to communicate anything you may want to communicate. So I will start by giving you a bit of an introduction to the Heat Pump Awards 2025 and the next application cycle. Starting from an introduction of the Heat Pump Awards. So this is a European Heat Pump Association project, and it's used to recognize the most efficient, smart, and sustainable heat pump projects at the local level. It was launched in 2011, and it's used to highlight cities and regions that have put in place energy efficient projects, which involve the use of heat pump technologies. And its international appeal has been growing year after year. You can see the statistics from since 2011, sorry. And this referred to 2024. So we have had 315 submissions, 37 countries have participated, and 301 cities have also participated. Here on the right side of the slide, you can click on the link for the website of the Heat Pump Award, and you can also check out the winning projects of 2023 and 2024 booklets, just to get a bit of an inspiration if you want to apply to this year. In the website, we have a very useful repository with all the projects from previous editions, both winners and applicants. There are multiple filters that can be applied when searching for a specific type of technology or solution, and a very nice map which shows where projects are located all over the world. They all represent precious examples of heat pump technology applications in real life, and recently also the Beyond Fossil Fuels campaign expressed their interest in a collaboration with us thanks to this database. So moving to the application process, it's very easy. You just need to go to the website and download the application template. You fill it out with all the information and resources, such as photos required, and indicate in which project category you want to submit your project. The application template is a PowerPoint presentation, and the idea is for you to use it as a way to showcase and underline the relevance of the work that has been done and the results collected by your project. There are 5 different award categories that to which you can apply. We have Heat Pump City of the Year, which is the category that recognizes heat pump projects implemented at the local level with the support of the city, always including the integration of heat pump technologies into city-owned utilities and district heating networks. Then we have the DecarBuilding, which is the category that honors projects that demonstrate smart and efficient uses of waste heat and heat pumps industrial processes, leading to a decarbonization of the industry. Of buildings, DecarbIndustry concerning the industry, and then we have lighthouse heat pump, which is a category that recognizes innovative projects that do not necessarily fit into the other award categories, but still represent a creative and unique solution to a problem using specific techniques and technologies related always to the deployment of heat pumps. Then you fill in the form with your contact information, and you attach the template, and you just click on submit project. So as I said, very easy. To give you a bit of an overview of the application cycle timeline, the applications opened on April 3rd. They will close on August 15th for this year, and results will be communicated around the 8th of September via email. For this year, we've also introduced some new features, such as the frequently asked questions section on our website, where you can find answers to any doubts you may have. And if you don't, you're always free to contact me directly by email. And then we also have an application template step-by-step guide, so that applying has never been easier. Here you have my contact information if you want to send me an email or give me a call. And now I will introduce our 2024 sponsor, Frascold. The presentation will be given by Kevin Norris, who graduated from Politecnico di Milano with a degree in energy engineering. He was previously part of Frascold's research and development department, where he developed a strong technical background. He has always had a keen interest in technical sales and market understanding. And now, as an application engineer in the sales department, he works to bring market demands into product development and assists customers in creating new products to support the energy transition and meet decarbonization targets. His quote is, "Capturing the world's beauty one click at a time, fueled by wanderlust and a passion for photography." Kevin, the floor is yours.
Thank you, Martina, for the introduction. Good morning to everybody. Today I will just introduce a little bit Frascold as company and our idea of innovation at the compressor level. You can, next slide. Frascold is a leading company that is in the market, in the refrigeration and heat pump, and recently in the heat pump market since 1936. We produce compressor, mainly semi-hermetic compressor, but also some open type compressor for this target application. We are an Italian company, so our headquarters is close to Milan. We have the production capacity of around 70,000 compressor per year. Next slide, please. We have also a worldwide footprint, so we have a partnership and direct system company all over the world. The main are in US, China, India, Vietnam, and we can also distribute our product with a lot of partners in all over the world. Next slide, please. Jumping more in the focus of the application, recently we received a lot of requests to jump from the standard, let's say, application of cooling and heating, residential, light industrial or commercial, to jump in deep industrial process to replace the gas boiler industrial process. We find out, I think that a lot of us that are in the industry know that the request of industrial heating up to 200 degrees is the majority of the request of heat in Europe. So it is a very big market that need to be decarbonized, and shifting from the gas boiler to the electrification, so using heat pump, is the target for the future. The main application are producing steam, producing hot air for drying process, waste heat recovery for pharmaceutical, food process, and all industrial process that involved to need to have some fluid above 100 degrees. Next slide, please. So our response to this market request was to develop new compressors that are able to withstand higher temperature, higher pressure in some cases. Here you can see all of our development, so that involved piston compressor starting from 4-cylinder up to 8-cylinder that are dedicated to mainly to air-to-water heat pump, also for the commercial, light industrial and residential application, to replace gas boiler even at, depending on the refrigerant, even at 85, or for with low density refrigerant up to 130 degrees. And the focus of this presentation, the screw compressor, that we develop 2 series that are able to give an answer to the market request to have a reliable system to produce steam, for instance, up to 170, as we see in the next slide. You can shift. Thank you. As said, we have 2 steps of the development. The first one is to deliver water or fluid at 140 degrees with different refrigerant. Can be natural refrigerant like hydrocarbons, or synthetic refrigerant like the 1,2,3,3-ZD. And with our range, we are able to produce up to 1 megawatt with this kind of system. Next slide. The second step is to produce water, and this is the most challenging, up to 100 pressurized water or steam or whatever fluid you need to heat up to 170. For this range of temperature, the only candidate of the best candidate is the hydrocarbons, isopentane or pentane. In this case, the capacity are a little bit lower, but we can produce up to 800 kilowatt of capacity. Next slide, please. Just an example of the envelope with isopentane. The light blue one is for the first step of the development to produce water or fluid up to 140, and the dark blue one envelope is for the second step of the development. Next slide, please. Just a section of how a screw compressor look like from the external point of view, and some components from the internal point. And as you can see in this slide, we wanted to underline what we change in the design of this new high temperature compressor. Basically, everything changed, excluding the external casing, the external cast iron. The main pillars of the development was a different motor that withstand higher temperature, and with oversizing of the windings, the oil, and what all is related to the oil, so the oil flow switch, the oil filter, the oil side glasses, basically also the electrical heater, because it needed to be heat up more than the standard process. The clearances to withstand and to absorb the thermal expansion going at this very high temperature. And of course, another very pillar of the screw compressor is the bearings. So are the bearings. So different cage material, and also in this case, the clearances and all the gaskets and O-rings of the compressor. So this compressor look like the standard one, but the design cover all the redesign cover all the components. Next slide, please. We have already some field tests up to 135 free, and some other are coming up. The main focus is North Europe, the area that I'm following as sales area manager, and one application in China. Next slide. For the second step of the development, we have a couple of installation, one still in laboratories, but quite ready to be put in field, and one already in field in a paper industry, producing steam for the process. So we are in the final step of the validation of the two projects. Next slide. Yes, this is for another picture of the laboratories, the test in the laboratories. Thank you for the attention, and keep in touch in case you have some question. I'm here.
Thank you, Kevin, for your presentation.
Thank
It's
you,
now
Martina.
time to welcome our 2024 award winners, starting from Joona Salmi, who is a project engineer at Turku Energia, focuses on energy efficiency, data-driven analysis, and smart energy solutions. He has worked on implementing fourth-generation district heating systems that boost flexibility and sustainability by integrating excess heat sources. His master's thesis explored the replication and the optimization of heat pump solutions for district heating, contributing to an award-winning concept that enables energy-positive districts through efficient surplus energy management. His quote is, "Advancement in the energy sector is not achieved through division, but through harmony, where diverse systems converge, enhance one another's strengths, and foster resilience through synergies." He's today presenting the heat pump integration into district heating and cooling network for excess heat utilization, Horizon 2020 response in Turku, which is the Heat Pump City of the Year Award winner. Joona, the floor is yours. Thank you.
Thank you, Martina, for your introduction. And as said, my name is Joona Salmi, and hello everyone. I come from Turku Energia. We are a local energy company in Finland, in Turku. And my presentation is about our Heat Pump City of the Year winning solution, which is part of this Horizon 2020 response project. Shortly about myself, as said, I am a Master of Science in Technology, and I have studied renewable energies and majored in energy efficiency. My current work includes energy efficiency improvements of the district heating in consumer devices and district heating systems. I work with also smart applications, and in addition, we have quite much heat pump solutions in our district heating network for different purposes with different applications, and this is one of them. And next slide, please. My agenda today is firstly to describe our conditions regarding the environment, infrastructure, and overall standards in Turku, Finland, and so on. And secondly, I give you a short review of our overall project in response, which in the heat pump solution is implemented. And lastly, we'll take a look to the actual heat pump solution and its energy balance, basically. Thank you. So, the city of Turku, in which I work, live, and our heat pump is located. We are located in the coast of Baltic Sea, in southwest of Finland, and we have a population of 200,000 and about 350,000 total in the near region. To set the full understanding of our requirements, I wanted to mention that our outside temperature level varies quite much throughout the year. Our lowest temperatures have been -25 in recent years and highest well over 30 degrees. And basically this creates a lot of challenges and requirements for the buildings and especially heating solutions. And it's also one of the reasons why these kind of projects are made and participated to ensure the energy availability at all times and also the environmental targets, such as the city of Turku's goal to be climate neutral by 2029. And shortly about Turku Energia, as said, it's my employer and is owned by the city of Turku. And we are one of the main factors in this climate neutrality target. We have over 200,000 end consumers in district heating, and we supply about 2 terawatt-hours of heat per year. And our district heating network length is about 660 kilometers. Our produced energy is 89% renewable, and about 30% of it was produced with heat pumps. We provide energy and related services in different forms, and in comparison to Middle Europe, it is notable that in Turku we haven't got any major natural gas supply or usage. So basically the available heating options usually are district heating, heat pumps, or direct electricity. Next slide, please. So shortly about the overall project, the Response project is funded by the EU's Horizon 2020 program. The overall objective is to create doable and especially replicable solutions in buildings or district level. The project emphasizes the integration of different elements from the urban environment and aims to create flexibility through interconnection of different systems. The main stage of the project is in 2 lighthouse cities, Dijon, France, and Turku, Finland. And both cities are actually famous for their mustard, but although I think Dijon is a bit more famous from it. In Turku, the main objective has been to achieve energy positive district, which produces more energy than it consumes. But it also has another objectives such as implementing new and novel smart energy solutions and city integration. It has to be said that there are also many different solutions than the heat pump solution which have been implemented in this district, but the main factor of this energy positivity target is the heat pump solutions, which uses the excess heat from this district cooling network's return side line. Okay, next slide, please. Next, I will describe the system's overall principle in a simplified manner. So this is the student village PED, Positive Energy District area, which consists of 5 blocks. There are new buildings from 2020s and older buildings from 1970s. And in this picture, you can see the Positive Energy District balance sheet and district heating line below the sheet. Left-hand side is our district cooling network, which normally supplies consumers with cooling. The district cooling network in this case gathers low temperature excess heat around the city and centralizes it to the Pasaia heat pump at approximately 15 to 17 degrees of Celsius. Opposite to the normal situation, the district cooling network supplies Pasaia with warm district cooling, return side water, and receives supply-ready district cooling. Usually it's the other way around when supplying district cooling. The energy from the district cooling network and return side is upscaled in this heat pump, and the heat pump supplies the heating energy to the positive energy district. The system is supported with Turku Energia's district heating network, which can receive the surplus heating energy from positive energy district. So it can supply, but it can also receive the heat to supply the surplus heat to the other places if needed. These both networks, district cooling and district heating, both work in two ways. So the dynamic and flexibility of the system is maximized. For this case, a dynamic tariff is created to enable more options for the system optimization and cost optimization. VTT, which is the Finnish government's technical research center, controls the whole system and has created an algorithm for the optimization of the system. This is made to gain the best possible efficiency in terms of costs and energy use, as said. The system is supported by the phase change energy storages, which stores the heating energy, and the heat pump is also fed with bifacial solar panels and supported by battery energy storage systems. Our target in this area is to achieve 120% of produced energy compared to the consumed energy. Currently, with minor setbacks in the deployment of other systems, we have achieved a little bit over 100, but the main test phase is still ongoing and is set to end next year. So I think we are going in the right direction. The heat pump share of this whole system is up around 80% at the moment of the consumed energy produced. Next slide, please. To further describe this system, I think it's better to describe the roles and responsibilities of different project partners. Need to be said that these partners are only the ones with the main role in this heat pump system. Other partners have also participated in the overall project, and there has been around 50 of them. But here are the main ones in this solution. So Högfors GST is a manufacturer of heat distribution devices and heating substation. In this project, they have built this substation, which basically connects two-way district heating and two-way district cooling together with the heat pump. This system includes DHAC, which is district heating after cooling system, which collects also extra energy from the district heating water after it has cooled. They have also included to the project additional and centralized heat recovery system to the exhaust air systems in all of the buildings in the area. Then there is Oilon, who has provided the heat pump for this system. The heat pump has around 400 kilowatts of heating power and 280 kilowatt of cooling power. It is a combination of two P150 units connected in parallel, which makes it P300 model with more suitable flow dynamics for this application. Then there is the VTT, which is the Finnish Technical Research Center. They oversee the system operation, controls the operation optimization algorithm, and implements research within the project. TYS, which is the Turku Student Village Foundation, in which premises this project is being conducted. Their main task is to perform on-site adjustment and conduct the user service. The user service has also been a big part of the project to include the habitants of the area. Lastly, Turku Energy, as we know already, supplies the excess heat to the site and enables the use of energy networks. We have also certified the heat energy to be 100% renewable for Pasaia, which is the building this is implemented. Turku Energy also provides technical support and is also in many technical aspects the representative of the city of Turku. For example, different studies and development plans and replication assessments has been conducted by Turku Energy within this project. Yes, next slide, please. I added a few links for more information about this project and especially the system. First, there is the Högfors GST article, which describes their work a little bit further. It also includes a virtual tour in the heating substation in Pasaia building. Then there is the project website, which includes further information about the whole project and the research in it. And thirdly, there is my master thesis about the replication of the system into the low temperature heating network. And also there is my contact information, and if you have any more questions after this webinar. I thank you for your time and wish you a happy and great summer. Thank you.
Thank you, Joona, for your presentation. We are now moving on to our third speaker, Ángel Carrera, who holds a physics degree from the University of Barcelona and joined Tecnalia in 2022. Previously, he worked as a project coordinator at Aiguasol Consulting and taught fluid mechanics, thermal systems, and HVAC systems at UPC and URL. His experience includes thermal energy system integration, district heating and cooling, building thermal rehabilitation, and statistical analysis for thermal system monitoring and grid services. His quote is, cascade heat pumps represent an innovative and efficient solution for renovating thermal systems in multi-family buildings while also integrating self-consumption of locally generated renewable energy. Today, he's presenting the Happening project, heat pumps in existing multi-family buildings for achieving the Union's energy and environmental goals, with a presentation happening in Pasaia, a cascaded heat pump solution combined with renewable energy and storage, presenting us the DecarBuilding Award 2024. Ángel, the floor is yours.
Hello, thank you, Martina, for your introduction. My name is Ángel Carrera, and I work at Tecnalia Research and Innovation, which is a research center in the Basque Country, north of Spain. And I'm working in concrete at the Thermal Energy Systems, which is a group that copes with a wide area of research, since thermal systems are very, very common in very different applications. We work in high temperature heat pumps at laboratory level, but also ice production for transport vessels or thermal management of electrical vehicles, district heating networks, I mean, wherever there is some thermal system. And I will be presenting now the results of the Happening project, which is an Horizon 2020 project that investigates the integration of cascade systems, cascaded heat pump systems in multiple components. As you know, in Southern Europe, we don't have infrastructures like district heatings, the one we saw now that Sami presented. So we are looking for other options as well in order to decarbonize this difficult system, this difficult sector, which is the multi-dwelling buildings. So if you can go ahead, please, Martina. Okay, well, I almost explained the background, then I will explain you what is the concept behind the project, which demonstration cases were developed within the project. In particular, I will be explaining the one we manage at Pasaia, and then the results and some conclusions for this work. Martina, please, thank you. Well, as you know, the buildings are a very big energy consumer in Europe, and mostly, at least in Spain, this consumption is mainly on heating and cooling demands, as well as domestic water, and it's majoritarily cooked by fossil fuels. The solution we propose it's to incorporate heat pumps in multi-dwelling buildings, which allow the decarbonization of this sector, but also shows synergies with other elements of the energy system, which will be relevant as well to the energy transition, and in particular photovoltaics and decentralized photovoltaics. Although the benefits, the deployment of heat pumps in multi-dwelling buildings, at least in terms of refurbishment of new buildings, it's marginal because of the difficulties to match with the needs of this sector. Okay, one of them is the use of high temperature emitters, which is massive in Spain, almost universal, I would say, for heat demand for space heating loads. And then the problems of the losses associated with a wide, potentially wide at least, losses in the distribution loads. So can you please go ahead, Martina? What we propose in the happening system is to incorporate in the dwellings a cascade heat pump system. One central heat pump keeps a neutral temperature loop, let's say, through the building, which is a concept very similar to the called fifth generation district heating. And then we use a thermal storage coupled to this centralized heat pump in order to store energy, thermal energy. This thermal energy stored can be generated by the surplus solar PV system owned by the building, or either use arbitrage in the daily market in order to optimize the invoice. The idea of the project was to maximize the renewable energy generated, but also consume it within the building. So to avoid an excess of surplus PV connected to the network, we found out that storing this surplus PV in a low temperature heat storage connected to the heat pump was a very competitive solution when compared to the electrical battery systems. The distribution loop runs at 20 degrees at each of the dwellings in order to minimize the distribution losses, but also this allows for the use of cheap flexible plastic pipes that can be installed quite easily compared with traditional distribution systems. And then each building has a individual heat pump, okay, which makes this second temperature lift from this 20 degrees to the temperature needed either for domestic water production or space heating demands. Next, please, Martina. So, well, in the project there were three demos, sorry, and each of those used a different approach to these cascade heat pump systems. There are solutions which have micro heat pumps, which use fan coils directly connected to the distribution loop. I mean, direct expansion fan coils. However, if you can go ahead, please, Martina. The system that I will explain you, it's this Pasaia system, in which the main focus was to maintain the existing space heating emitters, which are conventional radiators, as the one you see in the figure to the left, which often are operated here in Spain at something like 75 degrees or something like that. What we wanted to ensure is to keep the existing space heating heat emitters in order to minimize the disturbance to the residents of the building and also to minimize costs of the intervention. Please, next, Martina. Well, the building, which is at Pasaia, it's a social housing building owned by Alokavide, which is a public company that manages social housing in the Basque Country, and it has 8 dwellings. You can see these pictures. In the bottom left one is the building where we intervened, which is this 2-level building with 8 dwellings. The bottom right picture shows the previous installation that they had for space heating and domestic water production. The bottom one is the domestic water cylinder connected to the previously existing solar thermal system, which was not operating at the time of the intervention. And then they have also this individual gas boiler, which, as I said, is the main solution now in existing buildings in Spain. The project replaced those 2 elements and then incorporated their heat pump and a new domestic water cylinder, which come all together in a single equipment manufactured by EcoForest. It's a propane heat pump with a nominal power of 5.5 kilowatts. Next, please, Martina. So here is a brief scheme of the system. The system has 2 water heat pumps of 18 kilowatts connected to a central hot water storage of 2,000 liters, and then we distribute at something, well, it depends, but something like 20 degrees at this distribution loop. And then at each flat we have this water heat pump connected to the distribution loop, and which incorporates a 135 liters thermal storage, and then it also serves the space heating loop inside each dwelling. Then it's also a photovoltaic system with a fairly small battery. Next, please, Martina. This is a picture of the let's say the garage, the parking of the building where we could deploy this system. You can see in the center the 2 heat pumps, which take air from this grill. We had to make in the facade of the building. To the right is the 2,000 liter storage. This storage can be heated up to 70 degrees, depending on the forecasted demands and the availability of PV. So it can store a lot of energy when compared to the demand of the building in a very cheap and compact form. Next, please, Martina. This is the PV system that was already installed. And as I said, this is one of the strong points of the project, from my point of view, since it fits very well with the heat pump system, the decentralized PV. We will deal with it later. Next, please, Martina. Well, this is not the best photo, but you can see this is the intervention we made. It's too close, the right one. But we were able to fit in this previously existing space. This is next to the kitchen in a laundry room. And it's a very restricted space. But anyway, we were able to fit the system into the available space. So the only intervention in the building was to remove the gas installation, remove the boiler, remove the storage, and then directly connect the new heat pump. All the rest of intervention was done outside of the dwellings, except for a small connection to the kitchen. Next, please, Martina. Well, then we were able to have some monitoring data of the system during like 6 months, well, now a bit more. And here you can see what is the performance of the system as measured during this period from November 2023 to May 2024. The air to water heat pumps has a seasonal performance factor of around between 5 and 6, I would say, depending on the temperatures, which is quite high. And the individual heat pumps are running at 3.5 and growing slightly. There is some tweaks we were able to make in the control to improve a little the performance. So the overall COP of the system is something at around 2.6, which is quite good, I believe, for a cascade system. Next, please. This is the non-renewable primary energy savings. We have measured the gray values were calculated based on historical invoices. We had like 4 or 5 years of data of historical consumption of the building in terms of gas and electricity. And the green one is the measured primary energy consumption within these 6 months. So the average reduction in renewable primary energy consumption has reached 48% within the period, and it's especially high, I would say, during winter time. Next, please, Martina. And then regarding greenhouse gas emissions, the measured savings, taking into account the generation mix of the electricity system in Spain, it's a reduction of 75% of greenhouse gas emissions when compared with the previous situation. This is without taking into account the PV production, right? This is only in terms of the balance of the thermal system of the building. Next one, please, Martina. And then regarding the savings, we find out also with measured data, well, I mean, real invoices previous to the intervention, after the intervention, an average savings of 25% per building, per dwelling. It has to be said here that The baseline consumption of this building, it's quite low when compared to the average Spanish consumption. So extrapolating this to an average consumption dwelling in Spain, we would expect something like 250 euros yearly of savings per dwelling, right? In the case of Pasaia, it will be around 120, 150, but due to the low demands. And this is as well without taking into account the PV system. So if we incorporate this here, the savings could be much higher. And next one, please, Martina. So to conclude, the integration of cascade systems opens the possibility to the decarbonization of the the carbonization by the refurbishment of the systems in traditional buildings, let's say, in Spanish and in general Southern European cities. The coupling of the heat pump system with PV allows to I would say maximize self-consumption, which is great from a, let's say, global energy picture point of view, but also to drastically reduce the cost of storing excess PV in the central times of the day, which is something that is very important now to the Spanish grid. It's also interesting that we have a very low temperature distribution, so this means almost no head losses. But I would stress that this essentially reduces a lot the time to deploy the pipes within the building to something like 2 days or something like that. Very few walls have to be broken in order to pass the pipes, which is great. The COP of the system is quite high and also very stable, so there are no huge variations of performance due to time conditions. Every dwelling has the possibility to adapt the system to their needs and their existing heat emitters, and even allows the incorporation of a cooling device connected also to the load distribution loop. And then the key that we were looking at is the simplicity, minimizing interventions in its dwellings, minimizing convenience for the residents, and also reduces cost. We have used a very simple distribution layout, no balancing valves in all the distribution loop. Everything is balanced hydraulically, and we were able to maintain all the existing space heating emitters, which reduces a lot of the cost and is a supply for everybody. And that's all from my side, I believe. Thank you, Martina.
Thank you for your presentation, Angel. We can now move on to our fourth speaker, Steve Connolly. He has 40 years of experience in the refrigeration and heat pump industry in product design and marketing. His knowledge spans across the mechanical, electrical, and software aspects of all types of HVAC, but if asked to give a view on which part of it is the most interesting, it would not hesitate to point towards directly solarized cooling and heating machinery. In Steve's words, directly solarized cooling and heating is the hottest topic in the whole building services field right now, as well as being technologically fascinating, is just so compelling from an economic and ecological stance to run a building's cooling and heating services using DC power straight from the building's own rooftop solar arrays. He is today presenting the DC heat pumps with cross-connected PV project, which is the winner of the Lighthouse Heat Pump Award 2024. Steve, the floor is yours.
Thank you so much, Martina. And thank you everybody for listening. So I'll try to make my subject interesting. So as Martina introduced me just there, I think that we're moving into a world in the buildings field, we're moving into a world of systems. So I think there's a lot of innovation product by product, whether that's in a solar system or in a heat pump system or a chiller system, a chiller component. But we've taken a systems view of this. And if I just go through some of my slides, I'll lead you along the road that I've been along and share some of my thoughts. Can I have another slide, please? Okay, so the name of the game as I see it, and as my colleagues in the company see it, is self-sufficient buildings. Now, I caveat that because they can't be self-sufficient all of the time everywhere. That's probably not possible, but we want to get as far up that road as we can go, because we're trying to make genuinely low carbon, and that means we have to look at the electricity as well as the method that the cooling and the heating in the building takes place. The potential for self-sufficient buildings is huge, and the closer that you move to the equator, the more huge the potential is. So for example, it should be completely possible for supermarkets in the south of Europe, or further towards the equator, maybe Australia. It should be perfectly possible for them to run day after day after day entirely from their rooftop solar systems, so long as everything is configured correctly. Can I have another slide, please? So back to my opening statement there about the systems approach. We have as engineers also to be mindful of the constraints that we're working within, that are imposed on us by the electric system. All of our products run from electricity, which is potentially a good thing, but potentially it's a tricky thing as well. So I just give a slide there that shows the pressures on the electric system. So solar power is pushing more amps into the system. Car chargers are pushing more amps, taking more amps out of the system. Data centers, the growth of heat pumps, and so forth. So can I have another slide, please? So Ariba's solution for marrying up what I call the amp makers in the electric world, to marry up the amp makers with the amp takers, it looks conceptually like this. So within an HVAC system, cooling, heating, air movement, we have electric motors, lots of them, and by and large these electric motors are working from variable speed drives. And to remind everybody, a variable speed drive is a piece of equipment that takes a DC electrical feed and then converts that DC electrics into what I call artificial AC at different frequencies, and therefore the differing frequency gives you a different motor speed. So short, in simple terms, all of these motors in electric HVAC systems can be fed with DC, or at least their motor drives can be. And if all these buildings that host all of these electric HVAC systems are going to have solar on their roof or in their car park, then there's one heck of an opportunity to cross-engineer or co-engineer these systems. In particular across DC electric links, and also from a software point of view. Can I have another slide, please? So if you look at the pie charts just down there on the left side of the page, the one with all the different colors in there. If you look hard enough, you might see that I've added up all of the components of the HVAC world, so the heating systems, the hot water systems, cooling systems, fans and pumps. And this is old data, kind of before heat pumps. But you see already that this is in a typical commercial building. We have more than 50% of the electricity in the building going into is going to HVAC machinery, and as I've mentioned, most of this HVAC machinery is working from variable speed motor drives, and so that is one very large DC power consumer, amp taker. So we as a company have set about marrying together this trend in the market towards more solar and more heat pumps and more electric HVAC, more cooling, to make products that are packaged, pre-engineered. Can I have another slide, Martina? Thank you. And we're not so clever as to be doing this by ourselves. We're actually standing on the shoulders of the automotive industry. So if you look at that picture on the top left, you see a city bus, an electric city bus. So it's got a really big battery in there, which probably operates at 400 or 500 volts with some power converters, pushing it up to 700 volts of DC. And from that, we're running, in this city bus example, there are air compressors, there are air conditioning machines, hydraulic steering pumps, and other bits of machinery that are working from variable speed motor drives, which in turn are fed from a DC 700 volt DC link. So we've been inspired by that architecture. We've made our own version, and you see it there in that power panel down on the lower right part of the slide. You see we have there a package of variable speed motor drives, DC to DC power converters and batteries, and also DC to DC solar converters. So from that we can run individual HVAC machines, including heat pumps and chillers, or complete fleets of them. Can I have another slide, please? So as a company, we make everything. We have vertical integration. We're a small company, but we have become quite vertically integrated. Partly because when we began, we couldn't find a source anywhere in the market for DC power modules, and so we began to put a lot of research money into making our own. And then we thought, well, perhaps we'll just do that and put them into the market via somebody else's HVAC products, but that proved difficult as well because we're really in the early days of heat pumps still. So we ended up making chillers and heat pumps and solar systems and DC power systems that knit them together, and of course because of that we had to write our own software. So we are front running a market that's small today, but my hope, and I live ever in hope, is that this market is going to get very, very, very big, because the economics of running rooftop solar straight into HVAC is extremely attractive. The paybacks can be 15% faster if you, more than 15% faster if you power your HVAC equipment straight from solar, instead of pushing the solar just into the grid, into the AC grid. Can I have another slide, please? So this is, it's not come out terribly clearly, that photograph, but up on the left of the picture, you see that we make an integrated power converter system, which has got DC to DC power conversion, variable speed motor drive, and a port to connect on auxiliary variable speed motor drives. And from that, we can run refrigeration compressors, water pumps, condenser fans, air movement fans, and so forth. And then with our software engine in full play. And if you skip across to the picture on the right, you can see how we can actually manipulate the carbon intensity of the overall carbon intensity of the building's HVAC system by the amount of solar power we use, the amount of stored solar power we use from batteries, and the extent to which we either use the main power grid or avoid the main power grid. Can I have another slide, please? Now, a second reason we think that the market for directly solarized HVAC systems is going to grow is, and it relates really to the very fast paybacks compared with any other way of doing things, is that our products, we're not the only people doing this, we're the only people in Europe that I know of, but in China, there are some major brands who are already doing this at scale. And one of the attractive things here is that a pre-engineered, pre-validated system of solar and cooling and heating and software and potentially batteries too. We know what it's going to be. We don't have to reinvent it for each building. And in turn, as the green bonds wall of money, as I call it, comes into play and pays for more and more of the greening of the European building scene, then having a system that is pre-validated, pre-made, understood fully is much easier to collateralize in a green bond. And so this is an easier way to finance total greening of buildings than doing it piecemeal, heat pump at a time or a solar system at a time. We do the whole lot all at once. Another slide. Oh, that brings me to an end. I thought I had a different one there, but I don't have any more. So that, in a nutshell, is my presentation. Thank you very much for listening, and thank you, Martina, for inviting me along.
Thank you, Steve, for your presentation. We are now moving on to our fifth speaker, Michael Bantle, CTO at Aneo Industry. He's a subsidiary of the Norwegian renewable energy group Aneo. In this role, he is responsible for and operation operating heat pumps, specifically tailored to meet the needs of customers in the food, feed, chemical, and paper industries. With over a decade of experience in high-temperature heat pumps, energy efficiency, and waste heat utilization, Dr. Bantle specializes in steam compression cycles for industrial processes. He earned his PhD from the Norwegian University of Science and Technology and actively advocates for the adoption of natural refrigerants to drive sustainable innovation in the industry. His quote is, "Yes, we can. Steam generating heat pumps can efficiently deliver your process heat, making your operations both heat pump ready and future-proof." He is today presenting the Frigg system heat pump for the feed industry, utilizing moist air as waste heat, with the presentation how to deliver process steam efficiently using heat pumps, insights from first-hand experience. And the project is the winner of the DecarbIndustry Award 2024. Michael, the floor is yours.
Yes, thank you very much for your kind introduction. I think you covered most of it, so we can just jump to the next slide, please. Aneo is basically a renewable energy company, mainly situated in the middle of Norway, but we also have assets in Finland as well as Sweden. We produce and supply renewable energy up to 2 terawatt-hours per year, depending on the weather, basically from our windmills. And another 8 terawatt-hours upstream where we are producing electricity and have power and be basically carbon-free by clean energy from windmills. Downstream, we have 3 assets normally, where we also had our customers to be more energy efficient and basically decarbonize. So we have mobility, which is charging of electric vehicles, ANEO built, also charging of construction sites, as well as retail, where we work in the supermarket sectors. And the last addition to this downstream companies is basically ANEO Industry, which was established 3 years ago around the topic and about the ambition to decarbonize industrial clients by steam producing pumps. Next slide, please. When we talk to this industry clients, basically the topic is how to decarbonize and electrify their processes. There's always a different set of possible solutions, right? Becoming more energy efficient at the very bottom makes sense to using maybe electric boilers or on-site thermal generated solar thermal, geothermal, but maybe hydrogen is in discussion here. However, the all of these industries we talk to, they normally also have available waste heat, and their processes run in most cases on boiler steam. I think 70 to 80% of the industrial processes run on steam, not on hot water. So our idea and value addition to our customers is basically to heat recycling the waste heat and bring it back to their processes in the form of processed steam. On the next slide, we have a bit tried to outline how this can be done. It's basically you need basically 3 main technologies. One unit is the waste heat capture. That is waste heat, especially when it's air in the form of moist air, it's normally just blown away. So you have to install a sort of heat exchanger covering sensible as well as latent heat recovery. That's maybe the most important part of the technology. Then we have a second part of technology with a heat pump, where we then generate steam by a bottom cycle technology, by in our case with ammonia bottom cycle technology. And on the last part of technology, then just to take this generated steam and the required at the factory process. Yeah. If we make basically this loop from around the factory, we see that the waste heat energy is normally below 50 degrees, so we need to start our heat pumps at this kind of temperature, while the current boiler systems normally require up to 180 bars, 180 degrees or 10 bars of steam. Yeah. So what we cannot do is basically to supply 10 bar steam just because of the high temperature lift. Directly, we have to do what I call always in-depth integration, supply the steam as the lowest possible steam pressure to the process. So we basically also need this red line, which is going back to the factory, is basically a low pressure steam grid, which needs to be integrated and run parallel to the existing steam grid. But that's basically the 3 technologies which are required. Waiting for our pilot project fellowship in Trondheim. Next slide, please. Yeah, this is basically the Martina introduced. The heat pump system which we have installed there is producing 2 tons of process steam per hour. Also some hot water. That gives us a capacity, depending on demand, of 1.4 to 1.8 megawatt, which is the capacity that this heat pump can basically supply. And as I said, it recycles the waste heat from basically drying process. I'll come back to that a little bit later. And it's running at the efficiency, the COP of 3.0 for a temperature lift of close to 100 Kelvin. And I guess this is quite a good COP, and maybe also the reason why we got this award from EHPA. Next slide, I have outlined maybe the points why our customer was going for such a solution in cooperation for this heat pump installation. I mean, obviously, we improve the energy efficiency. The primary energy is demand of the factory goes down 60 to 80% in that range with every megawatt or kilowatt hour of waste heat that we are recovering and bringing back to the factory. That's, of course, a very interesting value proposition. There is basically where you can save money. Second point is obviously also to the reduction of the climate gas emission. This is, I think, the main motivation that our clients want to get away from gas boilers and reduce their climate footprints. And by doing it by heat pump, in particular in combination with renewable energy, we can achieve almost zero climate emissions. However, and this is, I think, maybe the main driver for most of the project that we have started, just with the grid capacity, we see that in Norway in particular, we have already a very high degree of electrification. So most clients simply, the first approach is, okay, we are getting rid of the gas or oil boiler and putting in an electric boiler, 10 megawatt, 20 megawatts. When they in the first phase of this project is quite often they realize that yeah, there's not enough capacity available, and in the future there will be even less chance of getting a 20 megawatt cable for a 20 megawatt boiler. So if you want to electrify, but if you have to use electricity and you don't get enough electricity that you need to direct electrify, you are ending up at a certain point to talk about heat pumps. And this was also, I think, one of the reasons why we got this this project here running, because this factory is in the middle of the city with a limited available capacity. So in order to expand their production, they need more electricity, more electric boilers, but there's not enough capacity available. And then it makes a lot of sense to move to a heat pump. Last but not least, we also apply only or whenever we can natural refrigerants. There's a strong lobby in Norway for using that, so we have to have we would need very good reasons not to use a natural media. And of course, with all discussions about HFOs and regulations and so on, and also the signals we get from the Norwegian Environmental Agency is that there might come in a ban on the HFOs. So by using natural working refrigerants, we also cover that aspect already today. Next slide, please. Yes. So this heat pump installation, as such, is reducing the electric grid capacity at this point here in the city center, close to the city center in Trondheim, by 1.2 megawatt electric, basically by utilizing the same amount of thermal energy from the existing. And in the current installation, with around 5,000 operational hours per year, we supply around 7.5 gigawatt hours of process steam and energy to the factory. And this pilot project was also the first one where we actually integrated this technology to this type of process. So it was also the aim and target to identify the best practice integration principles and operability for this kind of system, so we can roll it out to several factories as well. Last but not least, this was an aspect that we also discovered with our heat recovery unit. We are basically taking out sensible as well as latent heat. That basically means moisture, which we are condensing out, and by doing so, we also remove a certain amount of odor from the factory exhaust, which was there before. And yeah. This is basically the motivation for Fellesköpet to run this project and to get our heat pump on site. And Fellesköpet is a really large Norwegian actor in the agricultural sector, has around 4,000 plus employees and serves basically up to 40,000 farmers here in Norway. Next slide, please. Yes. So how did we integrate this heat pump? Basically, what is happening in this factory is also what is happening in every kitchen in a way. You get your raw materials on the kitchen table or into the factory. You start mixing them together according to a recipe, and at a certain point, here point 4, you start cooking it or basically adding thermal energy. In this factory, this thermal energy is supplied by direct steam injection into a mixing process, where then the product is thermally treated as well as hygienized. After that, this mass or raw material, now heat treated, is pelleted, basically sort of spaghetti machine. They make feed pellets, and then these feed pellets have a very high temperature, close to 80 degrees, and that in order to handle it further, it needs basically to be cooled down as well as dried in the cooling unit before it can be handled by the logistics department. And this is a basic setup right now. And as I explained before, today it's run on boiler steam, and the target here of our project and what we achieved is to substitute the boiler steam from its production lines by heat pump. This is on the next slide, where we basically have installed the energy recovery unit after the air filtration. At this point, the air has a humidity of around 35–40%, depending on the recipes, and temperature of 65 to 75 degrees Celsius. Then we start cooling it down and need to cool it down so far that we can actually get 1.2 megawatt out. And that means that the energy recovery temperature drops or goes down to around 35 degrees, and or even lower maybe, depending on the recipe. Then we take this temperature in the form, or this energy in the form of a water cycle, put it in our heat pump with an ammonia bottom cycle. From there we upgrade it to around 80 to 90 degrees. There we generate steam, and then we compress the steam up to around 1 bar G, plus a certain amount of superheat, and that is then injected back to the mixer and thereby substituting the current boiler. On the next slide, we also have maybe the most theoretical slide in this presentation today, where we try to outline why we basically using ammonia and at a bottom cycle and steam as a working media in a way in the open loop top cycle. This is basically the two lines. And if we compare COPs over certain temperature lifts for this system combination with other combinations, hydrocarbons or also other working medias, we see that it comes out in most of the case on top, meaning it's the most efficient combination for this temperature lift that we are covering with our heat pump, and that's a temperature lift from, let's say, 30 degrees up to 120, 130 degrees. So this is, of course, the reason, if you go to the next slide, why we can operate this heat pump with a really impressive COP of around 3.0 is what we always say for a temperature lift of 95 degrees plus minus. Yeah. This is in a way a good COP. It's a Carnot efficiency of more than 60%, and is very the main reason why we also get a quite okay project economic in our economic calculations together with the operational times. Yeah. One point is also too important to outline here, right? So the heat pump is one thing to supply, but this factory is operating with around, or running with around several hundred of different recipes, right? So every farmer and so on gets a different recipe for their particular feed product. That means we have a lot of new recipes, product changes in a way, and that is of course a challenge for production equipment when it comes to the heat pump, because you have to switch from one recipe to another. This means you have a slightly different waste heat temperature, but it can have a huge influence on the actual heat pump operation with respect to if you run it with 20 degrees or 30 degrees, or that has an influence on the COP, but also on the operationability as to how stable is the heat pump operating when you switch from one recipe to another. How much dead time do you basically get? And with the current concept, we really, and also integration, we have put a lot of effects into it to basically start the heat pump on Monday morning, have it continuously running while the factory does all the recipe changes until Friday. And this gives us then not only a COP, but it also gives us basically the gigawatt hour supplied over time. And one of the main challenges in the project was to minimize this dead time, basically, where the heat pump need to stop. And now we have basically 0 stops in the heat pumps. Yes, next slide, please. Here we see some pictures from the technical room. We basically have 2 rooms, where in the first room we have, here you see the ammonia heat pump system. with where we basically take in the energy at the 20-30 degrees on the left side in a way, and then we start compressing it up. And on the picture on the right, top right as well, to the left, you see heat exchanger where we start to generate steam as evaporating water while condensing ammonia in a way. And in the next slide, you see then that the steam is then further transported to the top cycle technical room, in which we just start compressing up the pure steam. Main difference is that once we are in the technical room for the turbo compressors, it's completely oil-free. We are just compressing water or steam basically up, and it has a bit different design requirements for technical rooms, make it easier to operate basically with MBR technology here. So, next slide, please. Already my conclusions. As I said, the project that we have presented here is a 1.5 megawatt heat pump with a quite flexible integration principle to be able to cover these different recipes in the factory. However, we see that the concept is recovering energy from sensible energy as well as latent energy from moist air is really widely applicable for different processes, drying processes and so on, where we basically achieve the same or have the same excess heat situation and also have the same temperature requirements. So we see that the next projects will most likely be directly connected to drying applications. We have also scaled this concept up to a 4.5 megawatt system, which is now in operation since also since 2024 in a fish meal factory, where we supply up to 7 tons of steam with up to 150 degrees. And that shows us also that with this concept, you really can target and get really in the range where you substitute medium to smaller sized boilers already today with market ready technology. And also for the more longer potential, right, we see that the waste heat is most often available by the industry in the form of moist air. There's not really exact numbers around that, but I would say at least 50% of the waste heat is moist air. And that means that we get this energy recovery temperatures and situations quite similar to the pilot project here, that can be adapted to different sectors, for example, paper industry. Also an important part that talked a bit that the steam pressure requirements, right? So substituting 10 bar boiler steam doesn't really make sense when you have to go with the heat pump to 180 degrees. If your excess heat is at 30 degrees, gives you a COP 1.5 or so, that's not really a good business case. But by doing this in-depth integration, we really have shown that most processes, in particular in the food and feed industry, don't need 180 degrees steam. They really can survive with 120 to 130 degrees steam if you do this in-depth integration. Yes, and I talked about the Carnot efficiency, 60% is our target. That helps a lot. And with that, I want to say, last slide, basically full steam ahead. I really need to outline that this project was a team effort, in particularly fellowship. It's a lot of work to integrate our concept in the factory side, and also our suppliers, EPCON and GEA, did a really good job to make this project run and work. So without them, we wouldn't be where we are today. So big thank you to them. And of course also to the Innova state subsidy. We got some additional money for bringing this pilot project into life. So I want also to thank them. Yes, and thanks to Martina for giving me the chance to present this on.
Thank you, Michael, for your presentation. We are now moving on to the last speaker, Dominic Silva, who is the EMEA marketing leader at Train Technologies, where she drives marketing strategies to boost awareness and demand for sustainable HVAC and transport refrigeration solutions. She's a mechanical engineer with a passion for climate innovation and storytelling, and she has held roles in product and brand management as well as enterprise innovation. Notable achievements include launching innovative heat pump lines in Europe and leading a global open innovation program. She holds a master's in mechanical engineering from the Technical University of Lisbon and a dual degree MBA from the University of Manchester and Kelly Business School. Her quote is, "Challenge what's possible for a sustainable world." And today she's presenting the Organon Thermal Management System with a presentation thermal management system with on-site heat recovery at large pharmaceutical plant, the project that won the People's Choice Award 2024. Dominique, the floor is yours.
Thank you, Martina. Thank you for this opportunity. And I know we're at time, so I'll try to do the express version here. So we can already jump over to the next slide so I can introduce the main players that made this project and award possible. So I'm part of Trane Technologies. One of our largest brands is Trane, known as a global solutions provider for heating and cooling equipment, including chillers, heat pumps, air handlers, basically anything that you would need for HVAC applications, as well as industrial process and cooling. So we have manufacturing facilities all over Europe, ranging from France, Italy, Germany, and Czech Republic, and employing over 4,000 people. And the project that I'm here to talk to you about was with Organon, more specifically their production facility in Oss, the Netherlands. It is their largest site globally, employing over 1,200 people. Organon is a global pharmaceutical company. What I personally love about Organon is that it is focused on improving women's health. So everything from contraceptives to drugs, etc., but just to focus on women. So Organon and Trane have been working for many years. It's been a long-term partnership. We've traditionally been their solutions provider for cooling equipment, mainly chillers. But recently we learned about Organon's ambition, Organon Oss's ambition to become carbon neutral by 2035. And this is what actually kickstarted a conversation about how we could help them achieve those goals by looking at heating and cooling combined. So on to the next slide. So the challenge that Organon Oss had was not just really a sustainability challenge, right? Having a commitment is tough. But one of the big challenges that they had was the fact that the biggest barrier to meeting their carbon neutrality targets was actually their heating plant. So today, they have a heating plant of approximately 8 megawatts, which is provided by 4 gas boilers. Due to the nature of their production facilities and the fact that they also have offices nearby, Organon has one of those profiles where heating and cooling is required all year round, whether it's summer or whether it's winter. The factory is right in the city center of Oss. It's a pretty big plant, as you can see from the picture. And what we're talking about here is a completely retrofit project, okay? So we're not talking about any sort of new build. And that means that we had to work with the space that is existing on the site. A lot of the chiller plants are all in the basement and with very uneasy access, let's say. So we had to take into account all of these challenges throughout the project. On to the next slide. So the solution that we found with Organon Oss was to essentially not just looking at, okay, how do we replace the boiler with a heat pump, right? Because that would definitely remove fossil fuel, the need for burning fossil fuel. But more specifically, we wanted to understand, are there other heat sources within your plant that today are completely not being used to their full capacity? And what we found is that, like most pharmaceutical companies, compressed air plants not only consume a lot of energy, but they play a huge role throughout the pharmaceutical processes. So compressed air requires cooling, right? Because you need to remove the heat once you compress the air. And so this, when you are rejecting air, basically that becomes an opportunity for you. So this was a heat source that we tapped into. So what we worked with Organon to do was essentially install 2 water-to-water heat pumps with a total capacity of 500 kilowatts using an HFO refrigerant, so almost 0 GWP. And we're using these heat pumps to basically cool down the compressed air. But rather than then rejecting this air to the ambient or a nearby ambient source, what we are doing is then feeding it back into the central heating network nearby. So the advantage of this is the heat is always available. So sometimes it's used for comfort heating. It can be used for other processes within the factory, such as cleaning, as an example. But in summer, they even have a need for heating just for the dehumidification of compressed air. So rather than having to activate a boiler to be able to do that, they can now reuse the heat coming from the water-to-water heat pumps. Now, production requirements obviously fluctuate. So this is why if you see the picture here of the water-to-water heat pump, you see a gray box, and that is our variable speed drive. And as one of the speakers before explained, the advantage of variable speed drives is that it allows you to basically match supply with demand so that you're always running at your optimal efficiency. And the biggest thing about the Train City, and this is what we developed the Train City water-to-water heat pump for, is that it is extremely compact. So it was really designed for these kinds of retrofit projects where you're able to simply roll in the heat pump through your normal doors, right, into the basement. No need to dismantle anything or pay a lot of money for the installation. So on to the next slide. Now, on the other hand, so this was focused on the production facility. On the other hand, we also saw an opportunity in their office spaces, which is right next to the plant. And here, there was actually an opportunity. So winter was coming. They had recently renovated the offices, and their calculations show that they required some supplemental heating, but they weren't really ready to invest in a full heat pump solution yet. Plus, there was still some construction going on. Plus, obviously investments is always a big deal when we think about CapEx. So the solution that the local plant manager found was to instead rent a heat pump of approximately 400 kilowatts, this time an air-to-water heat pump, so it would be installed outside. And this heat pump was then connected to a secondary coolant circuit. So the heat pump not only fulfilled the job, right, of being able to provide temporary heating while they needed it, but they actually used this trial period of approximately 3 to 6 months to build the business case and show not only can the heat pump actually deliver the same water temperature requirements as the boiler, but and without gas, obviously, but they were actually able to demonstrate that the energy bill was lower compared to previous years. So this was sort of accelerated to allow Organon OS to show to their leadership that they could decarbonize the heating for their offices by switching off the boilers and installing heat pumps instead. So the first phase has now been complete. They're looking to replace the remaining boilers gradually. And the biggest advantage of now replacing their boilers with a heat pump is that they are getting free cooling during the summer. So we know that it's very hard to depend on the climate anymore. We never really know. Summers are getting warmer, winters are getting colder. So this was a side benefit of additional comfort that they could offer their office workers during the summer. Next slide. So we've all been talking about numbers, so I wanted to be able to also show you the immediate impact. So this is the impact of phase 1 of the project. So by now, this has already expanded, but we were able to demonstrate that in the production facility, 7,700 gigajoules of energy were avoided. On the offices with the air-to-water heat pump that I just explained, that energy avoidance was around 3,680 gigajoules. And so if I translate this to ultimately the gas that they avoided, it was 243,000 cubic meters. And just like Michael explained before, right, like we go into this with the goal of, all right, we want to reduce the carbon footprint, we want to save energy, etc. And there's always the side benefits that kind of come out once the system is installed. So what we were able to see was that there was more clean air, right? And there's simple ways that you can see see that when you turn off your boilers, you're not burning fossil fuels, you don't have all the fine particulate matter in the air, and it can be seen as simple as your employees no longer having to clean the soot off of their windshields, right? Especially during winter. And another great thing about this project and the way that it was conducted, and actually we can already go to the last slide, Martina, and why, you know, I believe we won the People's Choice Award is because people were a fundamental part of the equation for success of this project, right? So technology is there. I think all of the speakers before me talked extensively to that, but to be able to decarbonize a facility like this, both on the production side as well as, you know, in the offices, you need the local involvement of stakeholders who are going to support that project, because change is hard. And yeah, change is hard. So on the production side, there was a very high level of engagement from the quality team, for example, because their concerns were to make sure that, you know, the water temperature would always be stable enough so that the product quality would never be compromised and they wouldn't run into issues around production uptime. But on the offices space, the main change behavior that they had to address there was really around the what do we perceive as comfort, right? So sometimes +1, +2 degrees make no difference for us as occupants, but they make a huge difference for the efficiency of the heat pump system. So really proud of the Organon OS team here. And in the picture, you can see Stan van de Staggen, who's the sustainability lead on a recent visit that we did there. Just to show that when you do challenge what's possible, it is possible to decarbonize. Heat pumps are a big enabler of that, but people are a very important part of that equation. So that's it for me, and I think I'll finish off on the last slide just with a quote, not from me, but from Remco Jansen, who is the HVAC project engineer that we worked with very closely for the design and installation of these heat pumps on the production facility side. And what I like about this quote, not going to read it because I'd never do it justice, is just every project is going to be unique. So every decarbonization project does require a very close partnership, and that's what we at Train are super proud and passionate about doing. So that's it from my side.
Thank you, Dominique, for your presentation and for kind of hurrying up since we are a bit late, but it's okay because all presentations were very well done and very interesting. We are now quickly and shortly moving on to the questions. So in the Q&A section, we have a few questions. Well, one was for Angel, but you already replied, so we can move on. We have 3 questions for Michael. The first one is, what are your thoughts on countries with a higher electricity to gas cost ratio? Do you foresee applicability for these projects in the future? And what factors could help drive their implementation in such countries?
Yes, I mean, for the higher electricity prices versus gas, that's obviously a problem. So whenever this ratio is higher than 3, we need to have our heat pump, when it have a COP of 3, will not give reduced OPEX, unless you have, of course, pricing in of CO2 taxation, or you price your emissions in a certain way, or you achieve state subsidies. So that is the hard truth at the end of the day, that as long as gas is cheap, everybody will use it, and that's maybe the main problem if you want to electrify.
Thank you. The next question for you is, does the MVR cycle require water purification before entering the steam compressors?
Yes, we require basically the same water quality as boiler steam. Maybe not so much for the actual compression, for which is happening in the turbo compressors, but really for the also where we generate the steam, we need pure waters, and everything which is impurities will in the way end up in the heat exchanger when you evaporate the water out. So we need the same quality as boiler steam in a way, and the same purification upfront to it. Yeah. But that's normally achieved without a problem because these systems are in place in the factories anyway.
Thank you. And the last but not least, always for you, is what was the payback ROI of the project?
Mm-hmm. I think for the pilot projects, we cannot really give you that number. We are still evaluating, and we also have developed this concept further into a more standardized, more compact system with lower capex. A pilot project is obviously maybe not the most cost efficient, but the next projects will have a normal payback time within, yeah, it depends on the energy prices, 5 to 6 years in a way. But the main driving factor is really the electricity prices and what you believe to be then 2030. So these payback times are a bit connected to that. However, we have proven that we can get the operational hours which we need to get the payback time. That is possible.
Thank you, Michael. We have one last question for Dominique. What is the temperature of the cooling water outlet from the air compressor station?
Yeah, I saw that question from David. I was trying to see if I could get the design specifications of this project at hand, but unfortunately I don't have it, so can't answer that right now.
Okay, and that was all for the no, wait. Another question for you, Dominique, that just appeared in the chat. What was the engagement with industry partner directly through Train or through an engineering company?
So the design and specification, right? The consulting work was done directly with Train, but then for the installation, we had a contracting partner.
All right, thank you very much for your replies. I believe this is it from the chat and the Q&A section. So I think we can close our webinar. Thank you for staying a bit over time. For those of you that stayed, you will all receive a follow-up email with the presentation of the webinar and the recording. And if you have any other questions or interest in the projects, you have all the contacts in the presentation. So feel free to reach out to our speakers or to myself as well. Thank you very much for your time, and I wish you all a very pleasant day and weekend since today is Friday.